Thank you for joining this webinar on the Advanced Materials Request for Proposals. My name is Ryan Reeves. I'm a materials scientist here at the International Space Station National Laboratory, and I'll be walking you through our RFP process and what we are seeking. We'll begin with this webinar with an overview of the National Lab itself, including its purpose and how you as a researcher might be able to use the unique facility that is the ISS to explore new research questions. Also included on our website will be webinars from commercial implementation partners who will describe in more detail their capabilities and facilities that they operate or support on the ISS. To give you background on us as an organization, we are a not-for-profit, non-governmental organization with the single purpose of facilitating research in low Earth orbit aboard the ISS. Our mission is to foster scientific discovery and technological innovation in space, expand U.S. leadership in commercial space, and inspire the next generation. To accomplish this mission, we work together with NASA, service providers, and commercial implementation partners. We draw on the research of the ISS to improve the lives of people on Earth and provide value to the nation, and create new partnerships across multiple disciplines. Broadly speaking, we act as space integrators to connect research and development organizations with platforms, engineering services, facilities, and funding sources. We've recently rolled out 2 new program focuses in advanced materials and industrial biomedicine. This advanced materials RFP is the first offering of that program. There's an additional industrial biomedicine RFP out at this time, and a webinar will be available on our website. Specifically for this RFP in advanced materials, we are soliciting project concepts for the ISS to enhance research and development of advanced materials and engineering. This is a pretty broad RFP on anything having to do with materials that can take advantage of the unique phenomena that occur in microgravity or exposure to space environment. The proposal should advance fundamental material discovery, design, synthesis, and characterization, or test material processes, strategies, and manufacturing methods. Overall, the project should use the unique microgravity aboard the ISS or the space environment outside of it to benefit life back here on Earth. So why space? For those of you who have not thought deeply about research in space, science conducted aboard the ISS is not solely about space science or space exploration. There are fundamental phenomena that can be removed in a microgravity environment that are just not possible to study in isolation here on Earth. The study of these phenomena, or the absence of them in microgravity, can then inform much of the terrestrial research, or in some cases, in-space manufacturing may be able to achieve that which cannot be done here on Earth. Specifically, the ISS provides a platform for 3 key research environments. First, the microgravity environment, where the near absence of gravity can have a significant impact on transport phenomena and solidification kinetics. Second, there's the extreme space conditions outside of the station. The space station environment outside provides a unique testing ground for exposure to things like radiation and atomic oxygen. Finally, there's the unique vantage point of the ISS in low Earth orbit. This allows us to look back on Earth to study our own backyard, or to look into space without the interference of clouds or the atmosphere. We envision that the first 2 environments, that being the microgravity environment and the extreme space conditions, will be most useful for you in your materials research. We'll look at the microgravity environment and its effect on various phenomena next. Conducting research in microgravity removes some physical phenomena. For example, the removal of buoyancy-driven convection eliminates the source of mixing and typically isolates diffusion as a transport process. In addition, the elimination of density-driven segregation often results in solutions and materials that are more homogeneous. Finally, the absence of gravity, you may no longer require a container to hold your fluids, such as a molten metal. This removes the effect of surface energies, surface tension, and eliminates nucleation at the interface, or the potential for impurities coming from the container. Each of these specific phenomena then has cascading effects on other transport and dynamic physics listed here on the right, everything from heat and mass transport to solidification kinetics. To give you an idea about how the removal of specific phenomena affects research, we've provided 3 specific research case studies. These case studies are intended to provide specific examples of microgravity research that have been done and are not intended to be fully inclusive of all of the research that can be done. This is mainly just to prime the pump of your research ideas. The first case is the effect of microgravity on the solidification of complex optical glasses. On the left, you'll see an image of Z-bland optical fiber, which is a mixture of fluorinated metals, including zirconium, barium, lanthanum, aluminum, and sodium. These metals have very different atomic masses, and therefore, in a gravity environment, compositional segregation of elements occurs during the drawing process and may lead to undesired crystallization. You can see by the picture on the left that the Z-bland optical fiber produced by NASA in a microgravity environment are optically transparent and homogeneous. The image there on the center, those are fibers produced here on ground, where you can see the fiber is opaque due to the presence of crystallization. This can also be seen by the SEM images on the right, where the top right image is a Z-bland fiber produced in normal gravity with a very rough crystalline surface, whereas the image in the lower right is a Z-bland fiber produced in microgravity and has a much more homogeneous and smooth surface. Currently, there are 3 separate companies which are investigating in-space manufacturing of Z-bland fibers through facilities operating on the International Space Station. These Z-bland fibers have significantly higher quality when produced in space, enough so to potentially justify the increased manufacturing costs associated with in-space manufacturing. Other similar areas where segregation and crystallization may be mitigated by a microgravity environment include bulk metallic glass, high entropy alloys, which consist of many metal elements with varying atomic masses, much like the Z-bland fibers, and therefore susceptible to the same segregation phenomena, as well as advanced ceramics. A second case study includes porous materials or foams, which may experience sedimentation or stratification during synthesis in ordinary gravity. Therefore, the synthesis of these multi-phase microstructures, like foam, in microgravity can achieve higher homogeneity of the pores in the absence of these phenomena. The image here on the right is of a metal foam fabricated by NASA in microgravity. The ingot on the left is the metal before it is expanded, and then the figure on the right is the metallic foam after it has undergone expansion aboard the space station. The results concluded that the microgravity improved the pore homogeneity throughout the metallic foam. You can then envision that applications of this might include battery electrodes, catalyst supports, separation membranes, or lightweight structural supports. Much in the same way that the removal of sedimentation and stratification improves metallic foams, you can see other areas of research where this phenomenon might be limiting here on Earth. These areas include other multi-phase microstructures, including polymer and ceramic foams, aerogels, porous catalysts or electrodes, colloids, emulsions, and liquid crystals, as well as self-assembled hierarchical structures. The final case includes biomaterials, where diminished convective flow in microgravity results in reduced shear forces when biological materials are produced. In the weightless environment of the ISS, this enables the design and manufacture of biological tissues in the absence of scaffolds or higher viscosity bioinks required in gravity. The image on the left here is of a RAS Lab synthetic muscle experiment that was conducted on station. The experiment largely studied the cumulative radiation exposure of synthetic muscle to the environment aboard the ISS. Another example of biomaterial experiments that have been conducted aboard the station include the fabrication of retinal implants by a Lambda vision, whereby the microgravity environment allows for a higher uniformity of layers during the coating process of the retinal implants. Similar areas of research in biomaterials include tissue scaffolding, implant materials, artificial tissue, cell material interactions, and bioprinting. There are multiple facilities existing on station to facilitate bioprinting in microgravity. In addition to the microgravity environment, the ISS provides access to extreme environmental conditions of space. These include the exposure to extreme heat and cold cycling, ultra-high vacuum, highly reactive atomic oxygen, high energy radiation, including ionizing radiation such as ultraviolet, X-rays, and gamma rays, as well as charged particles, and impact debris from micrometeorites. Test facilities exist outside the ISS to act as a test bed for material exposure to the elements of space. The range of materials that can be and have been tested span all of that encompassed by material science, ranging from metals and semiconductors to ceramics, composites, polymers, and biomaterials. For testing of material exposure and durability, areas of study may include accelerated degradation, contamination adherence, mass loss from radiation and atomic oxygen attack, or change in the material properties such as discoloration or reduced strength from radiation exposure. In addition to material exposure, power devices may be tested, and examples include photovoltaics and radiation-hardened electronics. You'll hear more about the specific facility capabilities from some of our commercial implementation partners. One of the key areas of your proposal development will be how to translate your ground-based research to facilities that can operate on station. Often the simplest route will be using existing facilities on the ISS. Here's a list of some of the research facilities that may be of interest for material science investigations. As you can see, there has been much work into facility development around solidification and crystallization equipment. In addition, there are thermophysical property facilities that can measure density, viscosity, and surface tension of materials at high temperatures. So for example, if you were looking at molten metals, this might be of interest for additive manufacturing or welding. More information on these facilities are available in the RFP as well as on our website. This is by no means an exhaustive list, and you are encouraged to contact our operations team as well as the commercial implementation partners who often operate the facilities for more information on how to translate your research to the ISS. The International Space Station National Lab coordinates with both NASA and commercial implementation partners to provide access to the station for research and technology development activities to benefit Earth. The commercial implementation partners provide a variety of services that not only include payload and hardware development, but also expertise in material science research. We encourage you to listen to the webinars of those commercial implementation partners and to connect with them regarding their services and access to facilities aboard the ISS. They can help you translate your research questions into a flight experiment. Our Advanced Materials RFP has recently opened and will now be open for a year. We are following a typical two-step proposal process. In the first step, you will submit a two-page concept summary. Concept summaries for the initial period must be received prior to September 30th. Concept summaries will be evaluated internally for operational feasibility and scientific merit. We will then invite those summaries that pass review acceptance to submit a full proposal in step 2. The full proposal will be by invitation only, and for the first period will be due January 6th. If selected, we will award a fully funded total scope mission, including launch, payload integration, in-orbit mission costs, data return, and if applicable, payload sample return. For more information on particular details of the RFP, proposals will be evaluated based on operational feasibility, scientific merit, and benefit to life on Earth. Before submitting concept summary proposals, investigators are strongly encouraged to consult with the National Lab Operations Team, whose contact information is here regarding capabilities and feasibility. Offers are also encouraged to work with a commercial implementation partner. We strongly recommend submitting letters of support to demonstrate feasibility and/or commercial interest where applicable. The ultimate goal of the ISS National Lab activities is to bring value and impact back to the U.S. economy and taxpayers by benefiting life here on Earth. The proposals submitted should demonstrate two key principles. The first is a pathway to benefit life on Earth, and the second is that the experiment takes advantage of the unique environment on the ISS, either the microgravity available on board the ISS or the extreme space environment outside of it. If research can be conducted terrestrially, it is usually more cost-effective and simpler to do so. However, there are key research phenomena that cannot be replicated here on Earth, and so the ISS serves as a great resource. Thank you very much for your time and your interest in this RFP. We believe that the ISS serves as a one-of-a-kind facility for research exploration. Included are links to our website where you can find more information and reach out if you have more questions. We'll be posting questions posed to us for this RFP on the website and posting those answers on the website as well. Thanks again for your interest, and we look forward to translating your research to the International Space Station.